Welcome to the engineering video series. In this tutorial, we will introduce the fundamentals of the Hoek-Brown constitutive model and demonstrate how to use it in GeoStudio for limit equilibrium and stress-strain analysis. In this video, we will explore the fundamentals of the Hoek-Brown constitutive model and the key principles behind it, how the Hoek-Brown model is configured in GeoStudio, including how to define the required material input parameters, a demonstration of rock slope stability analysis using the Hoek-Brown model in both slope W and sigma W, and a comparison of the results from the two analysis methods to highlight their consistency and key insights. The Hoek-Brown criterion is an empirical method for estimating rock mass strength based on the relationship between major and minor principal stresses. First introduced in 1980 for intact rock, it was later generalized to account for jointed and poor quality rock masses. Unlike the Moore-Coulomb criterion, the Hoek-Brown model captures the nonlinear shear strength envelope, which varies with effective normal stress. In its generalized form, the Hoek-Brown criterion expresses the relationship between the major and minor effective principal stresses, sigma 1' and sigma 3', at failure, as shown in this equation. The primary input parameters are sigma Ci, which is the uniaxial compressive strength of the intact rock, and the material constants, m sub b, s, and a, which together define how the strength is adjusted to reflect rock mass quality. In practice, the parameters m sub b, s, and a are commonly derived from the intact rock constant, m sub I, the geological strength index, GSI, and the rock mass disturbance factor, D, using the empirical relationships shown here on the right. The constant m sub I is a material property unique to each intact rock type. It controls the curvature and steepness of the failure envelope in the Hoek-Brown criterion, and physically it reflects the brittleness and frictional characteristics of the intact rock material. The geological strength index, GSI, is a classification parameter that links geological observations to the mechanical strength of a rock mass. It is determined based on the degree of structural interlocking and the surface quality of the rock. GSI ranges from 0 to 100, with values near 0 representing highly weathered, disintegrated, extremely poor quality or soil-like rock masses, and values near 100 correspond to intact, very strong rock with minimal fracturing and good surface conditions. For intact rock, GSI is taken as 100, which results in the material constant parameter S being equal to 1. The disturbance factor D represents the degree of damage and stress relief introduced into the rock mass by excavation activities such as blasting, stress relaxation, or poor excavation practices. Its value ranges from 0 to 1, where 0 corresponds to an undisturbed in situ rock mass, and 1 reflects a highly disturbed rock mass typically associated with heavy production blasting in environments like open pit mines. The Hoek-Brown model is integrated into GeoStudio for performing limit equilibrium slope stability analyses. Unlike the Moore-Coulomb model, the Hoek-Brown criterion produces a nonlinear shear strength envelope. In slope W, this curved failure envelope is used to determine the shear strength at the base of each slice. Because the limit equilibrium method is formulated in terms of the Moore-Coulomb strength parameters, cohesion and friction angle must be defined. To achieve this, slope W computes equivalent Moore-Coulomb parameters by taking the tangential slope of the Hoek-Brown function at the corresponding effective normal stress. The y-intercept of the tangential line represents the cohesion, while friction angle is determined by the line slope. Therefore, the equivalent cohesion and friction angle vary from slice to slice along the slip surface as the normal stress changes, reflecting the nonlinear nature of the Hoek-Brown failure envelope. The Hoek-Brown model is also integrated into GeoStudio for advanced stress-strain analysis. Its implementation is derived directly from the Moore-Coulomb framework and includes a user-defined dilation angle along with an optional tensile yield criterion. The nonlinear yield surface described by the generalized Hoek-Brown model is approximated using the Moore-Coulomb tangent at the current stress level, at sigma 3'. In the tensile domain, the Moore-Coulomb tangent at sigma 3' equal to 0 is applied. This formulation employs a non-associated flow rule for the Moore-Coulomb tangent approximation of the Hoek-Brown surface, while an associated flow rule governs the tensile yield surface. During each calculation step, sigma W compares the user-specified dilation angle with the instantaneous friction angle derived from the tangent to the Hoek-Brown envelope. The dilation angle used in the analysis is then limited to the smaller of these two values, ensuring numerical stability and physical consistency throughout the simulation. In this example, we consider a simplified bench-cut rock slope composed of two materials, sandstone in the upper section and limestone in the lower section. Both zones are modeled using the Hoek-Brown criterion. The objective is to assess slope stability using slope W with the limit equilibrium method, sigma W with the strength reduction method, and then compare the results. In our project tree, we have the two types of analyses already defined. Let us start by considering the slope W limit equilibrium analysis. This analysis uses the Morgenstern-Price method with the entry and exit slip surface search selected. The limestone and sandstone have been applied to the domain, but appear gray because their properties have not yet been defined. I will navigate to Define Materials and select the sandstone material. Here I will choose the Hoek-Brown material model from the drop-down dialog and enter a constant unit weight of 24 kilonewtons per meter cubed. I will specify the intact uniaxial compressive strength as 15,000 kPa and ensure the Calculated From option is selected, allowing the program to compute the Hoek-Brown failure envelope from the intact rock parameter, M sub I, geological strength index, GSI, and disturbance factor, D. For the sandstone material in this example, we will use M sub I equal to 12, GSI equal to 22, and D equal to 1, representing a very poor quality rock mass. The corresponding values of M sub B, S, and A are automatically calculated using the relationships discussed previously. If these parameters are already known, they may also be entered directly by deselecting the Calculate From option. Next, set the maximum confining stress, sigma 3, to 500 kPa. You can click View Graph to display the Hoek-Brown shear strength envelope based on these input parameters. I will now close this window and return to Define Materials to define the limestone, again using the Hoek-Brown material model. I will set the unit weight to 26 kilonewtons per cubic meter and the intact uniaxial compressive strength to 30,000 kPa. I will set the intact rock parameter to 12, the geological strength index to 30, the disturbance factor to 0.5, and the maximum confining stress to 500 kPa. Again, we can use the View Graph option to visualize the Hoek-Brown envelope for this limestone material. When we close the Define Materials dialog, we can see both material colors displayed on the domain with the assigned properties displayed in the materials table. Before we can solve the analysis, we will add the slip surface entry and exit ranges. I will go to Draw Slip Surface, Entry and Exit. Draw an entry line along the upper slope and draw an exit line at the lower slope. You can refine the coordinates in the entry and exit range window, for example, by setting the entry X range to 9 to 20 meters and the exit X range to 44.5 to 55 meters. After confirming the ranges, I will close the window. Next, let us move on to building the sigma W model for the strength reduction analysis of the rock slope. The first stress strain analysis in the project tree is an in situ analysis which will generate the initial stress state for the bench cut slope using the gravity activation option. The second stress strain analysis is a stress redistribution type of analysis with the strength reduction stability analysis method selected. The strength reduction factors indicate that the shear strength will be reduced in increments of 0.025, starting from an initial safety factor of 1 and continuing up to 1.5. We may need to revisit and refine these strength reduction parameters if the results appear insufficient. As with the limit equilibrium stability analysis, our materials have been applied to the domain but still must be defined. I will go to Define Materials, select the sandstone material, and in the Material Model dropdown, choose Generalized Hoek-Brown. The unit weight of 24 kilonewtons per cubic meter, specified in the limit equilibrium material definition, automatically appears. I will enter an effective elastic modulus of 2 × 10⁶ kPa and an effective Poisson's ratio of 0.2. In the strength section, the intact uniaxial compressive strength of 15,000 kPa also automatically appears, as this was the value defined in the limit equilibrium material definition. I will then specify the Hoek-Brown parameters m sub b equal to 0.0456600489, s equal to 2.2603294 times 10⁻⁶, and a equal to 0.53823676. These very specific values were copied over from the parameters determined by the limit equilibrium Hoek-Brown material definition using the intact rock parameter, geological strength index, and disturbance factor. These values must be explicitly defined in the stress-strain analysis. For verification purposes, the Hoek-Brown parameters should be the same regardless of the analysis type. Finally, I will specify a dilation angle of 5 degrees and deselect the tensile strength option. When this option is turned off, sigma W automatically applies the tensile strength derived from the Moore-Coulomb tangent approximation to the Hoek-Brown envelope at sigma prime 3 equals 0 in the tensile domain. If laboratory data are available, you can alternatively enter a measured tensile strength value directly with the tensile strength option selected. Now let us complete the limestone material definition. I will select the generalized Hoek-Brown material model, enter an effective elastic modulus of 2e⁶ kPa, and an effective Poisson's ratio of 0.25. I will specify the Hoek-Brown parameter m sub b equal to 0.428088792, s equal to 8.8426989 e⁻⁵, and a equal to 0.52234377. We will again specify the dilation angle as 5 degrees and deselect the tensile strength option. We have completed the material definition and can now solve all 3 analyses by ensuring that they are all selected in the Solve Manager and pressing the Start button to begin the calculations. Let us first consider the limit equilibrium stability results. The model displays the critical slip surface with a computed factor of safety of 1.45. In the slip surfaces window, the top 5 most critical slip surfaces are listed, but we can also choose to view all valid slip surfaces to see the full slip surface color map. From this, we can see that the slip surfaces with the lower factors of safety are concentrated within the upper sandstone material, reflecting its poorer rock quality. Next, I will click the graph icon and examine the convergence behavior by going to the factor of safety versus lambda plot. We can see a clean intersection point where the force and moment factors of safety converge at a lambda value of approximately 0.55. As previously discussed, slope W computes equivalent Moore-Coulomb parameters by taking the tangential slope of the Hoek-Brown envelope at the corresponding effective normal stress. 2 graphs were previously generated to see how cohesion and friction angle vary along the slip surface. When both cohesion and friction angle plots are selected together, it becomes clear that cohesion and friction angle vary in opposite ways. Cohesion increases to a peak before declining, while friction angle initially decreases and then rises. This pattern reflects the variation in base normal stress along the slip surface. The normal stress first increases along the slip surface and then gradually decreases, which in turn alters both the tangential slope and intercept of the Hoek-Brown envelope. We can confirm these trends by opening the View Column Information window. As we move from one column to the next, the base normal stress indeed first increases and then reduces, and both cohesion and friction angle follow the same behavior observed in the previous combined plots. Next, I will switch to the strength reduction analysis. Let's take a look at the lateral deformation near toe graph. This plot displays the x displacement of the selected nodes near the slope toe for all time steps. We notice that as the strength reduction factor approaches 1.375 to 1.4, lateral displacement increases sharply, indicating that the critical factor of safety lies within this range. The vector norm displacements graph plot shows the same behavior. The vector norm displacement changes drastically around a strength reduction factor of 1.375 to 1.4. Together, these graphs indicate a critical factor of safety in the range of 1.375 to 1.4, which aligns closely with the value of 1.45 obtained from the slope W analysis. To summarize, the generalized Hoek-Brown material model is available in both slope W and sigma W within GeoStudio. In limit equilibrium analyses, the parameters for the generalized Hoek-Brown equation can be automatically derived from the input values of m sub I, GSI, and D. The software uses the nonlinear Hoek-Brown failure envelope to compute the equivalent friction angle and cohesion. The friction angle and cohesion naturally vary along the slip surface, reflecting the curvature of the Hoek-Brown envelope. In sigma W, the nonlinear Hoek-Brown yield surface is approximated by using a Moore-Coulomb tangent at the current stress level. The formulation includes a user-defined dilation angle along with an optional tensile yield criterion. As demonstrated in GeoStudio, analyses performed in slope W and sigma W using the generalized Hoek-Brown model produce consistent and reliable results. This concludes our Hoek-Brown tutorial video. For further learning, please visit the Sequent Learning Center for online courses and documentation.